Where can I buy the pentose polysulfate?
That should work. I think that's working. Okay. Hello, everybody, to today's segment of TH2 Immunological Dominant Solutions. Today's segment, we're going to be discussing a concept that was coined and expanded upon by Professor Robert Navio called the cell danger response. This particular hypothesis is in which it postulates that the mitochondria alter their activity of respiratory chain dominance dependent upon the different varying degrees of stressors along the recovery cycle. So with no longer further ado, I will start today's presentation in sharing our PowerPoint slide and looking forward to hearing any feedback anybody may have along this presentation. All right. Yes, it seems as though all the social channels are connected. Sorry for the slight delay. Quite new to using a new software called Restream. So a little bit of a novice moment there with the broadcasting capabilities. But nonetheless, let's get started into the complexities of biomedical science, specifically in discussing immunological processes associated to TH2 immunological dominance. So before I get stuck into today's segment, segment 5, which is quite an interesting segment and it's one that's close to heart, as I'm a big fan of Professor Robert Navio. For those of you who had not attended previous segments, I'd like to give a bit of an overview and a recap. So within our first segment, we discussed the two major arms of the immune system, both the adaptive and innate immune system, discussing certain variables that each category has in terms of the type of immune cells, as well as the type of response, as well as a coordinated response that they have within an immunological symphony. Then we went into warranted Th2 immunological responses, in other words, healthy responses of a Th2 nature. Then we went into section 3, in which happens in Th2 dominance and the variables that contribute toward that. And then in the last segment, we discussed what impact Th2 dominance has in suppressing other immunological cells, which can lead to states of autoinflammatory or autoimmunity outcomes. So today's segment, we will be discussing the impact that Th2 dominance has on the cell danger response, as well as the impact that cell danger response 1 actually has in increasing the potentiation of Th2 immunological dominance. So exactly what is the CDR? Well, as you can see here by this diagram on the right of my screen, this is a concept that Professor Navio so eloquently put together after decades and decades of research into noting the metabolomic outcome that disease induces on a cellular construct, specifically impacting the mitochondria. So essentially, cell danger 1 is when the body is exposed to a toxicant, a form of stressor, whether it be a pathogenic stressor or an environmental stressor. And essentially, in that moment of perceived stress, what the mitochondria does is provides the immune system with a radical and a rapid form of available energy. And in doing so, creates an excess release of extracellular ATP. Now, ATP as a molecule induces inflammation the quickest in the body. Thus, when it is released in the extracellular space, it affords a increase or exacerbated increased release of inflammation, which is warranted in situations whereby there may be an infectious process, allowing the attraction of other immune cells to contend with whatever variable it may have been to induce that initial stress response in the first place. In the normal healthy healing cycle, this will afford an increase in attraction of initial innate immune cells, which will be able to detect a certain form of antigen, presenting that antigen in forms of different forms of antigen-presenting cells, such as dendrites and activated macrophage, to the point of which it will encourage a T and B cell response. At this point, it's a proliferated T and B cell response to which further presentation capacity through cross-presentation occurs, at which point more specific antibodies and specific type of T cells, whether it be initially T helper cells inducing a increased understanding of cytotoxic requirements, or potentially increased understanding of tolerance that ought to be induced by increasing T regulatory response. Whatever the response may be, that would lead into our cell danger 3, which is more targeted. It's like the snipers in the army that know exactly who it is that they're looking out for. So instead of going about and blasting the entire area, they take out the specific culprits that are causing the issue in the first place. And then once the threat has been contended with and been resolved, this is where we go into a healthy respiratory chain dynamic in which anaerobic glycolysis healthily feeds into the tricarbolic acid cycle, which healthily feeds into the electron transport chain in a means that affords minimal wastage of hydrogen ions and maximal shifting of electrons to afford a greater and higher ATP yield. Now, this is what is all to happen in any instance of physiological stress. However, what can unfortunately unfold is when that stress is in a perpetual state and the body finds it difficult to create a resolution. As an example, if there is a cell wall deficient variable that doesn't present as readily an antigen as a other form of bacteria, as an example, this may afford the body creating an ongoing CD1 response state in which we have a hyper release of histamine to create more chemo attraction, to try and get more immune cells to have quote unquote eyes on the situation, to try and improve upon the detection of what it is that they're finding it difficult to resolve. So certain instances, there can also be corruption that happens into immune cells, such as what happens with HIV, corrupting CD4 cells. And in that corruption, it creates an invasion to detection. And this can also lead to a hyper release of innate immunological activity, creating more perpetual inflammation. And in that perpetual inflammation, also unfortunately down regulates the efficacy of later or immunological variables that are meant to come into the equation later, meant to come into the equation to resolve what it is that the body is contending with. So in CDR1, essentially, mitochondria become somewhat hypoxic, releasing a lot of extracellular ATP. And in this case, in this state, there is a greater dependence of anaerobic glycolysis. Of which, if the anaerobic glycolytic systems are exhausted, can result in the poor formation of NADPH, as in it would compromise the efficacy of the pentose phosphate pathway, which leads to other variables of compromised red blood cell health and oxygenation in the body, which can often be seen in chronic disease states akin to, not akin, but associated to pseudo-hypoxia. And then when we get into the CDR2 state, this has often been associated with variables such as endometriosis, whereby there's just a proliferative response in the recovery of cells that have been impacted by former stressor variables. And this is where there is somewhat of a oxidative process going on, but there's a lack in the shunting of electrons in the electron transport chain, and there's a greater loss of hydrogen ions. So in this particular scenario, you actually have a surplus of inflammation happening that down-regulates often in insulin sensitivity and can incite metabolic resistance. And then we get into the third state here, in which there is autonomous oxidative phosphorylation, which essentially doesn't afford the most effective electron transport chain outcomes, as in the process of the electron transport chain, it is very much a question of balancing the intermembrane space to the outer membrane space and the enzymes that are involved in supporting how it is that hydrogen is shifted through different oxphos processes. And when it is that the oxidative phosphorylation processes are more autonomous, this can lead to a disparity in the availability of NADH or FADH due to insufficient NAD supply or due to compromised hydrogen availability in a higher oxidative state, which can actually, although there's an increase of oxidative phosphorylation, that increase of oxidative phosphorylation can lead to variables such as the premature release of cytochrome C, which creates a highly oxidative radical outcome, increasing other oxidative variables to come into the state on the cellular process, leading to an increase of congestion in the microvasculature. However, when it comes to Th2 immunological dominance, we're really considering the impact that histamine has on the microvasculature. And as we mentioned before, histamine most certainly opens up the body, can create leakiness to the body. It also excites the body. Small amounts of histamine or the right amount of histamine can improve upon variables such as libido. The right amount of histamine most certainly can neutralize extracellular threat, but an excess of it can lead to leakiness in the body, such as gastrointestinal hyperpermeability. So to this point here, other variables associated to CDR1 from a neuroendocrine perspective, an increase of beta amyloid accumulation is actually associated with high histamine release. Th2 dominance suppresses Th1 mediated neuroprotective responses, impairing the clearance of beta amyloid. Chronic oxidative stress driven by mitochondrial dysfunction exacerbates the release of oxidized mitochondrial DNA, which activates the NLRP3 inflammasome. This process attributes to or contributes to neuroinflammation, enhancing beta amyloid deposition in Alzheimer's disease. So essentially, in elevated levels of histamine, there are other variables such as glucose synthase kinase 3 beta that can also increase and further potentiate the likelihood of tau hyperphosphorylation, in addition to beta amyloid increase, which further just creates microglial reactivity in the brain, leading to a neuroinflammatory state akin to neurodegenerative outcomes such as Alzheimer's disease. Essentially, neuroinflammation and mitochondrial dysfunction amplify synaptic degeneration, especially when it is that myelin cannot be synthesized due to the high oxidative stress that histamine induces by congesting metabolomic efficiency, and through that congestion, heightening oxidative radical output, which reduces the availability of cortisol to be utilized for variables such as the recovery of the nervous system by means and production of myelin. Other variables, chronic intracellular infections, as mentioned in the previous segment, when there's a heightened Th2 response, the cytokine that are released in that particular scenario reduce cytokine that are required for a heightened Th1 outcome, such as interleukin 12 as an example. So in that suppression of certain cytokine that are meant to survey and detect what anomaly going on with inside the cellular construct, allows those anomaly to take hold and to proliferate. And this is especially important when it comes to chronic DNA viral variables, such as Epstein-Barr, most of which actually remain in a dormant state unless the immune system is compromised due to an exacerbated amount of stress exposure, at which point the immune system disarms its capacity to neutralize viral replication. Viral replication then hijacks ribosomal machinery, and in doing so can cause replication of itself, infecting neighboring cells and creating a spread. So reduced natural killer cell activity is one of those variables in which is suppressed in heightened Th2 immunological dominance. And this basically suppresses the immune system's ability to control intracellular pathogens, not only intracellular pathogens, but also cells that have become somewhat carcinogenic. Natural killer cells are incredibly important from an innate perspective to survey and ensure the inhibition or the cessation of oncogenetic processes in the body. Additionally, when it is that we cannot detect intracellular variables, there is an increased likelihood of carcinogenic cells to induce a localized angiogenic response, which can actually create somewhat of a process similar to a biofilm proliferation. And in that biofilm proliferation, the biofilm in and of itself can actually further heighten perception of extracellular threat, which compounds the histamine release, which only further worsens the immune system's potential capacity to be able to actually detect carcinogenic cells. So it's a vicious cycle that, if left unchecked, actually becomes more resistant to our own cytotoxic efficiency in neutralizing not only intracellular threat, such as fungi, Histoplasma caspillitatum, Candida albicans, Cryptococcus neuriformans, blastomyces, dermatitis, certain bacteria like chlamydia, rickettsia, mycobacterium, some parasites like Plasmodium, Toxoplasma, Babesia, or Cryptosporidium, and viruses such as Epstein-Barr, cytomegalovirus, and HHV6. All of which are considered to have intracellular pathogenic properties. Essentially, when it is that we cannot detect their presence due to heightened extracellular vigilance due to Th2 dominance, it impairs how it is that we can neutralize their removal. Mostly due to impaired interferon gamma signaling, which basically hampers macrophage activation, allowing the persistence of infections such as chronic Epstein-Barr. The expression of all this creates intracellular bacterial and viral infection persists, leading to systemic immune activation and metabolic burden, as observed in chronic fatigue syndromes or myalgic encephalitis. So we know that in instances of Th2 immunological dominance, due to that heightened activity, this leads to a disparity of vigilance in looking into the intracellular space. So we understand from an immunological perspective how it is that distortion can come into effect when one arm of the immune system is more active. Yet from a metabolomic perspective, what does this actually do to the mitochondria? Well, it actually causes mitochondrial dysfunction because in the microvasculature being somewhat congested due to microvascular fibrosis, this actually not only reduces the availability of substrate required for healthy membrane permeability and communication, but also the enzymes required in the communication between different components of membranes to afford healthy oxidative phosphorylated outcomes. So some of the mechanisms are here: sustained activation of the cell danger 1 response state inhibits mitochondrial oxidative phosphorylation, resulting in energy deficits and increased production of reactive oxygen species. This oxidative environment leads to the oxidation of mitochondrial DNA, perpetuating a cycle of inflammation and mitochondrial fragmentation. And this is really important because during processes of mitochondrial biogenesis, mitochondrial components are generally recycled, at least the healthier components are. Yet in this particular scenario, when the mitochondrial DNA is damaged due to a high oxidative variable, the availability of those components dramatically declines, and the efficiency of mitochondrial biogenesis also will therefore decline. So the expression to this is energy-intensive tissues such as neurons in the brain and muscles become dysfunctional. This leads to variables such as brain fog, memory loss, manifesting also in variables such as fatigue, reduced physical capacity, particularly reduced exercise tolerance or poor exercise recovery, and susceptibility to neurodegenerative conditions such as Alzheimer's in the way in how high histamine, by distorting insulin regulatory mechanisms, can potentiate the outcome of amyloid beta accumulation. It's very important to remember that amyloid beta is actually an antimicrobial. It's a natural body's response as an antimicrobial. And the reason why the body releases amyloid beta is a means to increase its capacity to detect variables that are creating an inflammatory distortion in the body. So it is yet another layer, dare I say, although it's not considered an antigen presenting cell, it is antigen presenting like. And however, if the issue is not resolved, the accumulation of that amyloid beta leads to being a plaque formation in the brain, which reduces glucose utilization in the brain, blood flow to the brain, and that can lead to other variables such as neurological ischemia, in inducing forms of pseudohypoxia, leading to neurodegenerative outcomes, not only that of Alzheimer's, but Parkinson's disease is also quite closely associated to the probability of Th2 ongoing excessive Th2 immunological dominance. Other variables to consider when it comes to the impact that Th2 dominance has on the cell danger 1 state is autoimmune dysregulation. Chronic Th2 dominance skews regulatory T cells, Tregs, and in doing so diminishes immune tolerance and promoting self-reactivity. So our Tregs really create a pattern interrupt and reducing the likelihood of our immune system actually attacking our own cells. And essentially, with Th2 dominance reducing our capacity to produce and express Tregs due to their being in the Th2 dominant state, a perception of ongoing threat. When there's a perception of ongoing threat, the body's not going to send a signal to calm its response to the threat, it's going to amplify the signal. And in that amplification of that signal, if it goes on for a long enough period of time, this does lead to poor pattern interrupt of the immune system, eventually attacking our own cells. Not only that, but also due to the way in which Th2 dominance affords damage to mitochondrial DNA, this can also lead to variables such as the release of cardiolipin. And when the cardiolipin is highly oxidized and released, this also affords an increase of damage-associated molecular patterns, which we had spoken about in previous segments, to be one of the major culprits, along with PAMPs, in inciting a high extracellular vigilant state, which affords an increased probability of polymorphonuclear leukocytes becoming heighteningly active, which can lead to an adaptive Th2 dominant state. So oxidized mitochondrial DNA acts as a damage-associated molecular pattern, or otherwise known as a DAMP, enhancing the activation of innate immune pathways and contributing to systemic inflammation. And how is this expressed in practical terms? Dysregulated immune responses manifest as autoimmune diseases, including in Th2 dominant status, lupus, rheumatoid arthritis, multiple sclerosis is one of them as well. Multiple sclerosis is more of Th17, but there are associations with multiple sclerosis having Th2 dominant-like symptoms and characterized by chronic inflammation and tissue damage. The most notable or the most notorious autoimmune disease associated to Th2 dominance would be that of lupus. Interesting thing about lupus and hormones, the FDA have been doing extensive research into the probability of high dosages of DHEA potentiating the reversal of lupus, particularly when its impact into the gastrointestinal tract. Obviously, the research is quite, dare I say, controversial, but insightful at the same time. It evokes a lot of interest, of which I myself most certainly am keeping an eye on. So if anybody out there that is struggling with lupus, do keep an eye out and see, on the latest research as to how DHEA is being found to actually support this cohort of individual. Cancer is yet another variable when it comes to Th2 immunological dominance. And that's just due to the fact that cytokines such as interleukin-4 and interleukin-13, which are heightened in a Th2 immunological dominant state, create immunosuppressive tumor microenvironments. This reduces the impact of our CD8 cytotoxic cells and natural killer cells to neutralize cells that have become carcinogenic or expressing oncogenesis, allowing tumor evasion from immune surveillance. The mitochondrial dysfunction in CDR1 further supports metabolic reprogramming in cancer. And as I mentioned to you, CDR1 is mostly associated to a dominance of anaerobic glycolytic activity, and which has been associated by in the past as the Warburg syndrome. So essentially, when it is that we get stuck in this particular immunological state impacting mitochondrial respiratory chain activity, this heightens the probability of anaerobic glycolysis, Warburg syndrome, to fuel sugar activity, of which most cancer cells have a propensity in favor of feeding off of. And this enhances tumor growth and metastasis occur as the immune system fails to eliminate malignant cells, but doesn't only fail to eliminate these cells, but actually potentiates their ongoing growth by means of how respiratory chain dynamics have altered to providing more readily available glucose stores. Um, Methylation depletion and Th2 dominance. So methyl donors are important for pretty much every process in the human biochemical or biochemistry, from that of how it's supporting detoxification to producing neurotransmitters to supporting hormonal formation, and just to say but a few, three of many a category. So essentially, what it is in our methyl donor pool, managing as such affords a healthy, balanced homeostasis. When it is that we find ourselves to be in a methyl deficient state, we may not be able to produce enough glutathione, as an example, which can lead to an excess of toxin accumulation. Not only that, but it can also lead to poor precursor availability required in Th2 dominance to support certain enzymes and genetic processes like histamine N-methyl transferase, which supports the degradation of histamine, so that when it is that we have an excess of histamine in increased activity HNMT, that at least creates a pattern interrupt to not allow that histamine to create further leakiness and inflammation in the body. However, depletion, methyl depletion and Th2 dominance are quite synonymous with one another. Th2 dominance increases histamine and allergic signaling, which can increase demand for methylation-dependent histamine clearance, like HNMT, like MAO-B, DAO increase as well, all of which require some form of acetylsomethene as a methyl donor. And this can lead, when we deplete our SAMI, essentially, this can lead to widespread compromise in the folate cycle. Chronic Th2 inflammation increases oxidative and immune turnover, diverting methyl donors toward glutathione recycling, DNA repair, immune cell replication, phospholipid turnover, and inflammatory mediator metabolism, thereby increasing methylation burden. So it really compromises how it is that we can even use phospholipids to stabilize membranes, increasing lipid peroxidative outcomes such as peroxynitrate. There's a wide-reaching effect that Th2 dominance has, not only on a macro scale and in impacting metabolic efficiency of thyroid functionality, but also on a microcosm and directly altering the membranes hydrophilic hydrophobic balance, leading to potentially saturation in certain contexts and also hyperpermeability and others. The outcomes of all this, from a neurotransmitter perspective, low levels of pteridine 4 or biopteridine lead to, and as well as an insufficient acetylmethionine, reduce serotonin and dopamine production, as well as norepinephrine synthesis. And this can lead to worsened mood disorders and cognitive impairments, depression, in certain instances, ADHD, with lowered serotonin, serotonin not only being important for that of our mood regulation, but also of that of our blood glucose utilization in the brain, can also lead to memory impairment. Glutathione, also in sufficient quantity and availability of methyl donors, leads to reduction of glutathione availability and reduced availability of folates and acetylmethionine and sulfate impairs glutathione synthesis. And this is not just important from a detoxification process, but it's also important from a connective tissue process. Sulfur plays a huge role in the production of glycosaminoglycans. And with insufficient glycosaminoglycans activity, this can really compromise the glycocalyx, which can lead to variables of atherosclerosis and other cardiovascular incidents that can come about from compromised glutathione production, as well as compromised sulfation or sulfur utilization. Nitric oxide, BH4 deficiency, and nitric oxide uncoupling decrease nitric oxide production, disrupting vascular health, immune responses, and neurotransmitter regulation. And polyamines, such as spermidine, acetylmethionine depletion impairs polyamine synthesis, affecting neuronal repair, immune regulation, and cell growth, i.e., low spermidine output. For those of you who are interested in any of the references, please note that they are cited here, of which it is that we were able to extrapolate much of this information. And these are quite interesting studies. There's one in particular, which was from with Capitis G in 2015, the neurobiology of tetrahydrobiopterin biosynthesis. Very good paper for anybody that's interested in understanding neuroendocrine dynamics of dopamine and how methylation plays or at least the folate cycle plays an intimate role in its expression. Continuing on with methylation depletion and Th2 immunological dominance, SUOX and SALT pathways, again, sulfation, SUOX pathways, sulfite toxicity. SUOX converts sulfite into sulfates. It's crucial for detoxifying sulfur-containing compounds. Oxidative stress and SUOX dysfunction in Th2 dominance leads to sulfite accumulation, which exacerbates neurotoxicity, consumes glutathione, and depletes antioxidant reserves. Additionally, that also impacts connective tissue and also blood-brain barrier permeability effects. Can lead to a compromised, very highly permeable blood-brain barrier, which also allows for other toxins to influence the central nervous system. This methylation interaction impairs SUOX function, increases oxidative stress, further taxing methylation pathways, and acetylmethionine-dependent detoxification. And salt genes, which are very important for detoxifying monoamines as well as estrogens, hormone and xenovartic metabolism, salt enzymes conjugate sulfate to hormones. And these are, for example, the detoxification of estrogens into warranted healthy metabolites instead of unwanted unhealthy metabolites. As well as the ability to metabolize the excess of monoamines to prevent excitotoxicity in the brain. So what does this all mean in terms of depleting the methyl donors in Th2 dominance? Basically compromises our hormetic bandwidth. And the more that we compromise our hormetic bandwidth, the shorter our state of, the more that we compromise our homeostasis, the shorter our hormetic bandwidth becomes, and the less tolerant we are to stress, meaning that things that historically seemingly would not have made us feel anxious or depressed can over time in these states lead to those exact unwanted outcomes of anxiety and depression. Feedback on glutathione and detoxification, sulfation inefficiencies amplify oxidative stress and reduce glutathione availability, impairing cellular detoxification capacity. And the more toxic we become on a cellular level, the less effective our cells are able to communicate between one another, which lowers our cellular metabolomic efficiency, and that leads over into the immune system, the nervous system, as well as the endocrine system. Which brings me to the next slide with regards to endocrinological outcomes of Th2 immunological dominance. And if we think about the impact that this has on the hypothalamus pituitary adrenal axis, essentially when there is an ongoing demand of inflammation, the body's going to try and quell that inflammation as best as it possibly can to prevent the likelihood of a necrotic tissue build-up. And one of the ways in which it does so is increasing the availability of cortisol. Cortisol is a very powerful anti-inflammatory hormone so long as it is available in its free-form state. However, when there is ongoing inflammation, the body will also reduce the impact that cortisol can have in creating down regulation to variables such as in the brain with the hippocampus. And how it does that is by increasing the activity of certain enzymes such as 11 beta dehydrogenase 2, steroid dehydrogenase 2, which converts free cortisol into inactive cortisone. In those particular scenarios, one can have elevated serum cortisol, yet feeling extremely exhausted. And when measuring saliva indexes or urinary indexes to measure the difference between cortisol and cortisone, it becomes apparent that there is a disparity in the free availability of actual cortisol. And this also occurs in states of obesity in which an increase of interleukin 6 also affords a maladaptive enzymic response, reducing the availability of free cortisol in order to try and neutralize the body's capacity to produce more energy, more heat, of which cortisol is also a mediator in the release of initial anaerobic glycolytic processes. The mechanisms of contribution, chronic inflammation, Th2 dominance, and persistent CDR1 promote chronic inflammation through elevated cytokines such as interleukin 4, interleukin 13, and interleukin 10. Interleukin 10 is actually a cytokine that can create immune tolerance, but when it is elevated in concert with interleukin 4 and 13, it can actually potentiate more histamine release, which leads to the inflammation in question. These cytokines interact with hypothalamic corticotropin-releasing hormone secretion, potentially leading to dysregulated hypothalamus pituitary adrenal axis activity. Excess glucocorticoid signaling, prolonged HPA activation results in hypercortisolemia. Sustained cortisol secretion suppresses immune feedback loops and further perpetuates Th2 immunological dominance. So essentially, when we have excessive cortisol, this actually compromises our natural killer functionality as well as our Th1 cytotoxic efficiency. Which is also a reason as why in certain autoimmune states, methotrexate is actually recommended to try and quell excessive activity in these particular arms of the immune system. However, ongoing concurrent suppression of these particular immune responses can lead to a proliferation of variables that are somewhat covert, hiding in the cell, leading to their replication and further corruption of our own cellular construct. And it basically is by down-regulating Th1 cytokines such as interferon gamma. Corticosteroid resistance, so chronic exposure, as I mentioned before, can actually not only attribute to the body's altered enzyme activity, neutralizing cortisol into cortisone, but the actual receptors to glucocorticoids can downregulate, the same as how it happens in insulin when there's an excess of insulin being released. Insulin receptors downregulate their sensitivity to the point where the body has to release more of the hormone to create the effect. And the same occurs when there is an excess of cortisol release. The body has to release more of it in order to initiate anaerobic glycolytic processes. This impairs the resolution of inflammation and promotes ongoing activation of the cell danger 1 response state. Manifestations as to what this results in is dysregulated diurnal cortisol rhythm, so compromised cortisol awakening response, which is really important because the cortisol awakening response feeds into the sensitization of the latter thyroid response in the day, which subsequently also feeds into a parasympathetic response later on in the day in improving sensitivity of GABA receptors. So essentially, it's a cause and effect, and it's a sequential process of which if there is a pattern interrupt or dysregulated function in one of those junctions, can lead to a dysregulated outcome in further sequences, compromising sleep architecture, in which a person may find it difficult to wake up in the morning, but have an excess of energy in the evening, finding it difficult to wind down and get to sleep. And a lot of this has to do with the immunological state, which may be potentiating compromised adrenal response, leading to chronic fatigue syndrome or a wired but tired state. Anxiety, fatigue, and insomnia, all due to altered state stress response and glucocorticoid feedback mechanisms, and increased susceptibility to chronic inflammatory and autoimmune conditions. Must remember, when it is that the body cannot neutralize a threat, it's going to try to compensate by proliferating its response to neutralize that threat, to the point where it becomes completely dysregulated and loses its responsivity, leading itself into a state of reactivity. Endocrinological outcomes of Th2 continuing from before, the hypothalamus pituitary thyroid axis. So increased cytokine-mediated inhibition leads to reactive oxygen species, which interferes with the way in how the hypothalamus releases thyroid-releasing hormone secretion, and in such impacting the pituitary's release of TSH. In certain instances, there might be an exacerbated release of TSH that can occur from this, to the point of which there is insufficient response that happens from an exhausted pituitary thyroid connection. Often interleukin-6 and tumor necrosis factor alpha suppress deiodinase activity, reducing the conversion of thyroxine into active triiodothyronine. Mitochondrial dysfunction, oxidative stress can persist from persistent CDR1, impairs thyroid hormone receptor function, and this is on the cellular construct, particularly impacting uncoupling protein 3, which is an essential step in oxidative phosphorylated 4 in the electron transport chain, which basically leads to a shortfall in the management of hydrogen in the proton pump gradient, leading to poor ATP output, but also premature leakage of variables such as cytochrome C, or the potential thereof. This reduces cellular responsiveness to thyroid hormones, and this is where a person can have normal thyroid labs, but yet have hypothyroid symptoms, because on a cellular state, the signal is not being received appropriately, as well as, and mentioned before, in heightened states of neutrophil activity, which is predominantly a Th17 response, but also has ties into Th2 being a polymorphonucleoleukocyte, can deplete copper stores in the mitochondria. And when there's insufficient copper in the mitochondria, this leads to poor cytochrome C reductase activity, which also compromises the battery, the mitochondrial battery analogy, leading to poor energy management and maintenance in its expression. And this basically, it can impact how the mitochondria supports, or how the thyroid support mitochondria, in that even if thyroid hormone was to stimulate UCP3, if the substrates required in the precursor phases of oxidative phosphorylation aren't sufficient, then this can lead to a disparity in T3, not creating the most optimal energy gradient, but actually inducing more of a hyperproliferated inflammatory response. So it's not just about the hormone or giving the hormone, but it's also about ensuring that there is enough of a balance of nutrient profiling to support enzymatic reaction that T3 may amplify on a cellular level. Thyroid autoimmunity, dysregulated Th2 responses, and T regulocyte inhibition create a favorable environment for autoimmune thyroiditis, such as Hashimoto's. Elevated Th2 cytokines exacerbate the production of thyroid autoantibodies. What does this manifest in? Low T3 syndrome, euthyroid 6 syndrome, reduced free T3 and elevated reverse T3. Hypercortisolism is quite notorious for increasing reverse T3, as well as certain cytokine like interleukin-6 and TNF alpha. They all as well as interleukin-4 and interleukin-5 to a certain degree, can also increase the production of reverse T3. And the reason why the body does this is to try and slow down its metabolic machinery in a state where there's just too much heat because inflammation is not controlled effectively. Symptoms of hypothyroidism such as fatigue, weight gain, weight loss resistance, cold intolerance, constipation, despite normal or mildly altered TSH levels. I would never wholly rely on TSH as a means to determine thyroid activity, and nor would I also just rely upon T4 or T3 marker indications, but rather take them into account and looking into the metabolomic systems that that thyroid hormone is responsible for, namely looking into cardiovascular specific markers like your lipogram variables and your red blood cell variables, as well as taking consideration variables such as copper, and iron utility in the body, of which triiodothyronine plays an intimate role in the production of protein carriers to support their transport effectively throughout different regions of the body. Continuing on potential hypothyroid episodes and autoimmune cases with transient thyroid toxicosis. The thyroid toxicosis is more of an impact of an autoimmune state, but that again, in instances whereby the immune system becomes reactive, this most certainly can alter how the liver actually processes and metabolizes certain thyroid hormone, leading to the impact there of thyrotoxicosis, specifically on the central nervous system. And that is the end of the fifth segment of Th2 immunological dominance solutions. I hope that you all enjoyed this segment today. I see that we have a few attendees here with us. I will allow the opportunity for any of you to ask questions. If you have any questions to ask, but please don't feel obliged to do so. But I will please feel you all have been given opportunity to unmute your microphone. If you feel if you have something you'd like to expand your understanding on, go ahead and ask. Okay, great. Well, hopefully I was very clear in my explanation of the impact that Th2 dominance, or the bidirectional impact that CDR1 has on Th2 dominance, and that Th2 dominance can have in perpetuating a CDR1 state. And I look forward to catching up with you all again next week, Thursday, which we will be going over the sixth segment of this 9-part series, in which we will be discussing the impact that Th2 immunological dominance, which we'll be discussing the solutions to improve mitochondrial thyroid receptivity that becomes distorted in states of Th2 immunological dominance. From me, Justin McGuire, thank you very much for attending today's segment. It's truly appreciated. And for those of you who couldn't make it, in reviewing this video, if you have any questions, please feel free to either email me or to send me a direct message on different social platforms. I always make an effort to try and share knowledge in the best possible way to empower those who are going through a health challenge or know people that might be going through a health challenge. Until we meet again next time, guys, please stay well and remember to try and stay optimized. Take care. Bye now.